Somewhere at the edge of our solar system, more than 3 billion miles from the sun, one world has been quietly stealing pieces of its neighbor's atmosphere for millions of years and staining itself red in the process. Nobody saw it happening in real time. Nobody caught the moment it started. There was no single dramatic event, no explosion, no impact, nothing a camera could have caught. In the act, it has simply been happening quietly and continuously for longer than either world has had anyone around to notice. But in a series of papers published in 2025, using data from the James Webb Space Telescope, scientists finally confirmed what was going on between Pluto and its largest moon, Charon, and the mechanism behind it turned out to be something that exists nowhere else that we have ever found in the entire solar system. This is the story of how astronomers finally separated two worlds that had been blurred together in our instruments for decades, and what they found the moment they could finally tell them apart. To understand why this discovery took so long, you have to go back to July 2015, when NASA's New Horizons spacecraft became the first, and so far, only human-made object to fly past Pluto up close. What it found tore up almost everything textbooks had assumed about a small, frozen world sitting at the far edge of the planetary neighborhood. Pluto was not simply a dead ball of ice, it had mountains made of solid water ice, standing as tall as the Rockies. It had a heart-shaped basin, informally called Tombaugh Regio, containing a vast plain of frozen nitrogen. Named Sputnik Planitia, its surface broken into irregular polygonal cells that told scientists the ice underneath was slowly convecting, churning like a pot kept just below a boil, evidence of ongoing geological activity on a world many scientists had assumed was long dead. And wrapped around all of it, it had an atmosphere, a real active atmosphere, thin as it was, made mostly of nitrogen, with traces of methane and carbon monoxide. New Horizons photographed something nobody expected to see on a world this small and this cold. A blue atmospheric haze rising more than 125 miles above the surface, stacked into at least 20 distinct layers, backlit by the sun in one of the most striking images the mission ever returned. Pluto, it turned out, had weather, but a flyby, however spectacular, only ever gives you a single frozen moment. New Horizons screamed past Pluto in a matter of hours, capturing an extraordinary snapshot, then kept going out toward the Kuiper Belt and beyond, never to return. Whatever it saw once. The haze was there, photographed and confirmed, but why it existed, what it was actually doing to Pluto's climate, and how it behaved over time were questions no single flyby could ever answer. Those questions needed sustained, long-term observation, and I trained on Pluto not for a few hours, but across years, ideally from an instrument sensitive enough to pick out details that had eluded every telescope pointed at that distant patch of sky before. In 2017, years before that eye existed, a planetary scientist named Xi Zhang at the University of California, Santa Cruz, made a specific prediction based on the New Horizons data. If Pluto's haze was behaving the way certain models suggested, absorbing sunlight during the day and radiating that energy back out as heat at night, then the haze itself should be detectable by its own thermal glow in mid-infrared wavelengths, completely apart from anything reflected off Pluto's icy surface. It was an elegant idea. It also could not be tested, no telescope. Operating at the time had both the sensitivity and the resolution needed to actually pick out that specific signal because of a problem that had frustrated Pluto researchers for years, a problem named Charon. Charon is enormous compared to Pluto, roughly half its diameter, orbiting so close that the two bodies are more accurately described as a double system than a planet and a simple moon. Charon is enormous compared to Pluto, roughly half its diameter, orbiting so close that the two bodies are more accurately described as a double system than a planet and a simple moon. Pluto and Charon are locked together in mutual tidal lock, each permanently showing the same face to the other, orbiting a shared center of mass that actually sits in the open space between them rather than inside Pluto itself, a genuine binary relationship unlike anything else among the major moons of our solar system. And where Pluto turned out to be geologically alive, with flowing ice and an active atmosphere, Charon looked, at first glance, like almost everything scientists had expected Pluto itself to be before New Horizons arrived. A quiet, heavily cratered world of water ice, cut across its Pluto-facing hemisphere by an enormous chasm system reaching depths of more than 4.5 miles, evidence of an ancient upheaval when Charon's icy crust cracked open and was partly flooded by a slow-moving ice-based form of volcanism. Charon has no atmosphere of its own, nothing to generate weather, nothing to drive the kind of haze process shaping its neighbor, and yet, sitting at its pole, it carries a feature that has nothing to do with anything Charon itself ever produced. From the distance of Earth, even through powerful telescopes, Pluto and Charon's thermal signals blur together into a single, indistinct smear of infrared light. Trying to isolate the specific thermal glow of Pluto's haze from that combined signal was, in the researcher's own description, like trying to identify one instrument's individual notes inside a wall of noise. Zhang's prediction sat there, untestable, for 5 years, waiting for an instrument that did not yet exist. That instrument was the James Webb Space Telescope. Not, contrary to how some headlines have framed it, seeing Pluto for the very first time. Webb had already been observing Pluto and Charon since 2022, in the years immediately following its launch, as part of a dedicated study of the system using its mid-infrared instrument, known as MIRI, tuned to detect wavelengths between roughly 5 and 28 microns. What made 2022 the real turning point was not that Webb looked at Pluto for the first time. It was that Webb's 21-foot mirror, the largest ever launched into space, finally had enough resolving power to do something no previous telescope could manage: cleanly separate Pluto's light from Charon's, cataloging each world's thermal signature on its own for the first time in the history of astronomy. And the moment researchers pulled Pluto's signal apart from Charon's, Zhang's 5-year-old prediction was confirmed almost exactly. The faint infrared glow of the haze showed up precisely where the model said it should. Then, in May 2023, MIRI turned back toward the system and captured something even more valuable: a full, high-quality mid-infrared spectrum of Pluto and its atmosphere, spanning nearly 5 to 27 microns, a spectral range that had simply never been explored before at this level of detail because no earlier instrument had the sensitivity to make it worthwhile. What came back from that spectrum, combined with the earlier thermal measurements, gave scientists their first real, detailed portrait of exactly what Pluto's haze is doing, hour by hour, as the dwarf planet rotates. The picture that emerged describes something researchers say does not resemble any other climate system found anywhere else in the solar system. During Pluto's day, haze particles high in its thin atmosphere absorb solar energy. Then, as that same patch of atmosphere rotates into night, those particles radiate the stored heat back out into space with remarkable efficiency, cooling the surrounding gas far more effectively than gas molecules alone ever could. That cycle repeats every single Pluto rotation, acting like an invisible thermostat, constantly pumping heat out of the upper atmosphere and keeping temperatures far colder and more stable than earlier models, built without accounting for the haze, had ever predicted. In some of Pluto's atmospheric layers, the haze's cooling effect was measured at roughly 30 degrees Celsius beyond what previous models expected, a genuinely significant swing for something as commonly overlooked in planetary science as a haze layer. This matters because Pluto's atmosphere, made up mostly of nitrogen with traces of methane and carbon monoxide, should, by the simplest models, respond to sunlight the way most thin planetary atmospheres do, warming somewhat during the day and cooling somewhat at night, following the gas itself. Instead, the haze particles appear to be doing most of the actual thermal work, effectively decoupling Pluto's temperature swings from what the gas alone would produce. Researchers involved in the work described what they were looking at as effectively a new kind of climate, something unique in the solar system, an atmosphere regulated not primarily by gas, the way Earth's, Mars's, or Venus's are, but by solid haze particles acting as the dominant thermal control mechanism. That alone would have been a significant enough discovery to justify years of waiting for the right instrument. But buried inside the same data was something stranger, something that turns this from a story about one world's climate into a story about two worlds quietly exchanging material across empty space. Pluto's atmosphere, thin as it is constantly leaking. Its gravity is weak enough, and its atmosphere active enough, that gas molecules, including methane, are continuously escaping into space rather than staying gravitationally bound the way Earth's atmosphere does. That escaping methane does not simply vanish into the void. This part of the story, in fact, is not entirely new, and it is worth being precise about who found what and when. Back in July 2015, when New Horizons swept past Charon, it photographed something nobody expected on Pluto's largest moon, a striking dark reddish region capping its north pole, roughly 375 miles across, so visually strange that the mission team nicknamed it Mordor Macula, after the blackened land in Tolkien's fiction. Every other polar cap scientist had ever observed anywhere in the solar system was bright, coated in reflective ice or frost. Charon's was dark and red, and nothing about the moon's own chemistry explained why. In September 2016, a team led by Planetary scientist Will Grundy published an answer in the journal Nature, built on the New Horizons data. Their proposal was that methane escaping Pluto's atmosphere was drifting across the roughly 12,000 miles separating the two bodies, freezing onto Charon's pole during its decades-long winter darkness, then being chemically cooked by ultraviolet light and the solar wind into reddish organic compounds called tholins, slowly, staining the ice a color that did not belong to Charon at all, but had traveled there from its neighbor. It was, As one researcher on the team put it, as if Pluto were spray painting its own moon. What the James Webb Space Telescope added in 2025 was not the discovery of this exchange, which had already been proposed nearly a decade earlier. It was a far more precise, physically grounded account of exactly how it works, tying the amount of methane capable of escaping Pluto directly to the behavior of the haze thermostat driving the dwarf planet's own atmosphere. Once, researchers had a strong hypothesis built from a single flyby and years of modeling. Now, with Webb able to isolate Pluto's atmospheric signal on its own and measure its mid-infrared spectrum in detail, they had direct and ongoing confirmation of the mechanism actually driving material off of one world and onto the surface of another, and a working model for how that process connects to the same haze particles quietly regulating Pluto's temperature. Once methane reaches Charon, exposed to solar ultraviolet radiation with no atmosphere of its own to shield it, that captured methane undergoes a slow chemical transformation, breaking down and reforming into complex reddish organic compounds called tholins, the same broad family of molecules responsible for the reddish coloring found on other icy, methane-rich bodies across the outer solar system. The result is visible on Charon's surface right now, dark, distinctly reddish caps at its north and south poles, material that did not originate on Charon at all, but arrived there, molecule by molecule, drifting across space from its much smaller neighbor. Researchers describe this interaction, atmosphere escaping one body and physically staining the surface of another, as something that happens nowhere else that we have observed in our solar system. Moons orbit planets everywhere, but a genuine ongoing transfer of atmospheric material from one body directly onto the surface of its neighbor, altering that neighbor's chemistry and color in the process, is, as far as current observations show, unique to the Pluto-Charon system. Charon has no atmosphere of its own to speak of, and yet its polar regions carry a visible signature written by its neighbor's air. Scientists studying Charon's polar staining had actually proposed this exact mechanism years before Webb's data arrived, based on earlier modeling and lower resolution observations. What the 2025 papers did was confirm it directly, using Webb's mid-infrared measurements to build a far more precise picture of exactly how much material is escaping Pluto, how it is distributed once it settles onto Charon, and how that process connects to the haze thermostat driving Pluto's own atmospheric behavior in the first place. The haze does not just regulate Pluto's temperature. By helping determine how efficiently gas molecules like methane can be lifted high enough in the atmosphere to escape Pluto's weak gravity, it plays a direct role in how much material eventually makes the journey across to Charon at all. One process, driven by particles most people would never think twice about, is simultaneously keeping one small world's climate stable and slowly redecorating its neighbor's poles. There's a reason this research matters far beyond the Pluto-Charon system itself, and it has to do with a period in our own planet's history that long predates complex life. Before Earth's atmosphere became rich in oxygen, a transformation that did not begin in earnest until roughly 2.5 billion years ago, our planet's air is thought to have been dominated by nitrogen and simple hydrocarbon chemistry. Not entirely unlike Pluto's atmosphere today, just far denser and warmer. Some researchers studying early Earth have proposed that a haze not unlike Pluto's may have once blanketed our own planet, similarly influencing surface temperature and shielding fragile molecules like ammonia from being broken down by ultraviolet light before life had the chance to make use of them. Organic hazes of this kind are thought to have played a delicate balancing act on any early world that had them absorbing enough radiation to protect sensitive prebiotic chemistry without trapping so much heat that the surface became inhospitable in the other direction. Understanding precisely how a haze layer manages that balance on a small, cold, well-studied world like Pluto gives scientists a real physical benchmark for how thick and how active such a blanket needs to be before it flips from a warming effect to a cooling one. An insight that feeds directly into models of how early Earth's climate might have actually behaved, and by extension, into how scientists evaluate hazy atmospheres detected around distant exoplanets today, worlds where a similar haze layer could mean the difference between a surface capable of nurturing the first steps toward life and one where the chemistry never gets the chance. None of this is finished science either, because Pluto is not done changing and Webb is not done watching. Pluto takes 248 Earth years to complete a single orbit around the Sun, which means the observations taken so far in 2022, in 2023, and again in 2025 have only captured the very early stages of a long, slow Arctic winter settling in at Pluto's North Pole. As that winter deepens over the coming decades, and as Pluto continues drifting farther from the Sun along its long, elliptical orbit, researchers expect the haze thermostat to work even harder, compensating for steadily falling sunlight, a process Webb is positioned to keep monitoring across the years ahead in a way no previous mission ever could. That kind of long baseline monitoring is something New Horizons, moving past the system at more than 30,000 miles an hour in 2015, was never built to provide. A flyby captures a single chapter. Webb, sitting in a stable orbit nearly 1 million miles from Earth with years of operational life ahead of it, can watch the same story unfold, scene by scene, checking back on the same haze, the same escaping methane, and the same slowly deepening red at Charon's pole, across a meaningful fraction of Pluto's actual season cycle for the first time in the history of this kind of research. Scientists are also running laboratory experiments back on Earth right now, freezing precise mixtures of methane and nitrogen under Pluto-like conditions, trying to recreate the unusual haze grains directly and measure exactly how efficiently they absorb and release heat. Work meant to refine the same models, Webb's observations are already testing from 3 billion miles away. Combining that laboratory work with Webb's ongoing infrared monitoring gives researchers something rare in planetary science, a genuine feedback loop between what is being measured on a real, active world and what can be recreated and tested, atom by atom, inside a chamber on the ground. Step back and look at what actually happened here, because it says something bigger about how much of what we think we understand about our own solar system is still limited by the instruments we happen to have pointed at it. For years, an entire physical process, methane escaping one world, drifting across open space, and physically altering the color of another world's poles, was sitting there, fully real, fully ongoing, strongly suspected since 2016, but never confirmed with real precision, simply because no telescope on Earth or in orbit had the combination of sensitivity and resolution needed to pull two overlapping infrared signals apart and measure exactly how the mechanism actually behaved. It was not hidden by distance or by mystery in the way headlines sometimes like to suggest. It was hidden by blur, a technical limitation, not a cosmic one. The moment Webb's mirror was large enough and its instruments sensitive enough to separate Pluto's glow from Charon's, an entire climate system revealed itself in detail, sitting in a signal that had, in some sense, been reaching Earth all along, just never with the clarity to actually read it. It is worth sitting with how strange the basic fact of this really is, even once you set aside all the technical detail. Two small frozen worlds, sitting roughly 3 billion miles from the nearest source of heat and light, are locked in a relationship where one is very slowly, continuously bleeding its own air onto the face of the other, and has been for as long as either world has had the atmosphere and gravity needed to make it happen. Likely millions of years before any human instrument existed to notice, Charon's red cap is not decoration. It is a running record, written in tholins instead of ink, of exactly how much of Pluto's atmosphere has drifted across that gap and settled onto its neighbor over time. Every year that passes adds a little more to it, and Webb, for as long as it keeps watching, will be able to track that record continuing to grow. Pluto and Charon are still out there right now, still locked in that same slow exchange, one world's air quietly settling onto its neighbor's ice, one haze layer still rising and falling with every rotation, still keeping a small, frozen world's climate stable against the cold of deep space. Webb is still watching, and there is still more of the story left for it to tell. If this is the kind of story you want more of, subscribe, and let me know in the comments what surprised you most about Pluto and Charon.